Now we address the issues of thermodynamic systems and work. Okay. Um, and to start, so we define a thermodynamic system as any quantity. This is going to be a little generic, but any quantity or system where we have thermodynamic quantities or properties of interest. Okay. So, what we mean by that is any system where we're interested in things like the temperature, pressure, volume, internal energy, the work done either by the system or on the system or something like this. Okay. So, suppose that we have a container with a piston, a movable piston, um, and the container, inside the container is gas particles. Okay. So if it's this gas and its properties, its total mass, its density, its temperature, pressure, volume, internal energy, the velocities of the particles on average, all of those kinds of things, then this is our system. Okay? And the container represents the boundary, and then the surroundings around the container are the environment, or you can either call them surroundings or environment. It doesn't matter. Okay. Um, so the reason we need to make these distinctions, okay, is because um, we need to be able to determine whether our system is closed or whether our system is open. Now, a closed system, okay, is a system that is completely separated from its environment. An open system is not. Uh, separated from. Now, the reason this is important to note, okay, is because what this really means, if my system, and it doesn't have to be gas, it's just that gas is a really, really easy example to work with, okay? Um, a closed system has no energy exchange with its surroundings. Okay? Whereas an open system has energy exchange. So what this means is if your system is open and your environment and your system are at two different temperatures, there will be thermal exchange between them. Okay, there will be heat exchanged between those two, well, between the system and the environment. In a completely closed system, no energy exchange occurs, and so no heat flows from the system or into the system. Okay. Now, so an example of in practice, let me put it this way: in practice, there is no such thing as a truly closed system. Okay. But approximations can abound. Okay, so a simple example that a lot of people use would be something like a thermos, right? So you want to keep a drink cold on a hot day, so you have a thermos, and you put ice in your thermos as well as your drink, and you take it with you wherever you're going, and it should stay really, really cold for a really, really long time. So that is an approximately closed system, the way your thermos is designed, and the same is true if it's a cold day and you put a hot drink in, right? The idea being to keep your drink hot. But no system in practice is ever truly closed because we just can't make completely perfect seals, right? We can't seal off our system from the environment perfectly, right? But we can get reasonably good approximations, and for a lot of cases, we will use the approximation with really good results, right? To a really good approximation, there are certain systems where this is a really good model. But open systems, okay, and a really good example of an open system would be like your kettle or your pot on the stove. Those are not closed, even though you can have something like soup or trying to boil water or something in a kettle or a pot on a stove. The boundary allows heat transfer from the environment, i.e., the stove, into the system, right? And it's usually because the pot is made of metal, which is thermally conductive, um, and that allows the heat to then flow into whatever's in the pot, right? So an open system is the general rule, although a closed system can be well approximated in many circumstances and is highly desirable in certain circumstances, especially when you're trying to make careful measurements on how, say, if I change the volume of my gas, how does its pressure respond and how does the temperature respond? I want to have that sealed off from the environment as much as possible to make those measurements. Okay. So this is what a thermodynamic system is. All right. And we can assume, okay, that when a system has been left alone, and this is true whether the system is open or closed, okay, as long as the system has been allowed to exist for a certain length of time, then the system will be in what we call equilibrium, okay? And this just means that on average, all of the particles have the same essential properties. There aren't particles that have different pressures inside the container, okay? You don't have a temperature gradient inside the container. And if your system is allowed if your system is open and it's allowed to exchange energy with its surroundings, then eventually, after a long enough time, it will come into equilibrium. So this would be like your cup of hot chocolate or coffee sitting on the counter. After a long enough time, it comes down to room temperature because it's been exchanging energy with the room as the environment. And would therefore be at the same temperature, and you wouldn't have a temperature gradient through the cup of hot chocolate the way you would in the case as it's coming into equilibrium. The liquid at the bottom might still be very hot, while the liquid at the top might start to cool off, and you might get a temperature gradient inside the cup until all of that thermal energy has been exchanged, and then the cup is in equilibrium with its surroundings. Okay. So the next thing to address is this issue of work. And again, we're going to use our container with the piston. Okay, and again we have gas particles in here. Okay, and so the gas is initially at pressure P1, at volume V1, and at temperature T1. Okay, but now suppose that I push downward on the plunger with some force, and I move the plunger down some distance delta x. Okay, so I've pushed down the plunger some distance delta x, and I give the system some new thermodynamic properties. Okay, so first things first, remember that work is equal to force times displacement. So a small amount of work, delta W, would be equal to the force pushed down times my displacement. For our purposes at the moment, it doesn't matter if we call it W or delta W. They mean the same thing. They're a quantity of work that was done. But if I think about letting delta X become extremely small in the limit that delta X goes to 0, then this becomes a derivative. Or I really should say a differential. Okay. But remember that pressure is equal to force divided by area. And so my force is my pressure times my area. Okay. So the pressure that the gas exerts on the piston times the surface area of the bottom plate that's in contact with the gas would have to be the force. Okay. So, and by the way, since our force is the only way to direct a force that has a component that can allow the piston to move is in the downward direction. So that allows the dot product to go to 1, right? The cosine of the angle between f and dx becomes 1. And so we can write this as f dx, and inserting our pressure and our area. Okay. But a dx is the volume of the displacement of the piston. That is the volume the piston was displaced. So this leads us to an important result. Work will be done when I have pressure and my volume changing. Okay. So what this really means is this equation is solvable if we then integrate between our two volumes. So the idea here is that we need to find pressure as a function of volume. And there's one readily available example that is easily calculable that lets us do this, and that is the ideal gas law. So if we assume that the gas inside this container is an ideal gas, then we know that PV equals NKBT. This is the form of the ideal gas law that I prefer, but it doesn't really matter. You could use lowercase n times r times t. It doesn't matter. But the idea is that if I divide both sides by my volume, then my pressure is written as NKBT divided by V. And now I have my pressure as a function of my volume, and I can now integrate. So, for example, right, let's actually do a hard example here. Let's suppose okay, so here's our two relevant equations. Okay. So let's suppose that our initial pressure was 1 atmosphere, for example. Which is 1.01 times 10 to the 5th pascals. And let's just let V1, I don't know, be 0.1 cubic meters. Okay. And then I compress the volume by a tenth of or a 1/100th of a cubic meter. Okay, so I compress it 10% from 0.1 down to 0.09. Okay, so how much work was done? Okay, so if we perform this integral, my work is going to be equal to 0.1 cubic meters, from 0.1 cubic meters to 0.09 cubic meters, NKB times T. We need to specify the temperature. Yeah, so let's suppose that the system is kept at a constant thermal, it's in constant thermal contact with an isolated bath, and let's say, I don't know, 300 Kelvin. Okay, so the temperature in this particular example isn't going to change. Okay. So now we need to solve this integral, right? But if NKB and T are all constant for this particular case, then they come out of the integral, and I'm left integrating dv over v, and this turns into the logarithm, right? And the reason it turns into this, okay, if I do this integral from, let's just say, v1 to v2 dv over v, this is the natural log of v from v1 to v2, and that becomes ln v2 minus ln v1. And then by the property of logarithms, we can say that this is the natural log of the quotient. Okay, so that's the steps that fill in the gap from here to here. Okay, and let's just say we have 1 mole. So 6.02 times 10 to the 23rd. Okay, so then this becomes 6.02 times 10 to the 23rd atoms. 1.38 times 10 to the negative 23. This is joules per Kelvin. And 300 Kelvin times the natural log of 0.09 divided by 0.1. Okay. And if we perform this calculation out, we will get, give me just a quick second here. Okay, so this calculation just the coefficients of NKBT give us 2492, essentially 0.3 joules. Atoms is unitless, and Kelvin cancels with Kelvin, and so we're left with joules. And notice that the natural log of 0.09 divided by 0.1 is also going to be unitless, because it's a volume over a volume. And so if I take 0.09 divided by 0.1 and take the natural log of that, it is negative 0.105. And notice I'm carrying out more sig figs in this intermediate calculation, but that's perfectly fine. We'll round at the end here. So 2492.3 times negative 0.10536. So negative 262. 0.58, well, 0.59. And so if I round this to, if I assume all of these are 3 sig figs, then we'll round this to 3 sig figs. So this becomes 263. And that is joules. Okay, so that is the amount of work that was done. Now, For the moment, don't worry about this negative sign. Okay. In the next lecture, we will really detail out what this negative sign means and how to handle it. Okay. For the moment, just worry about the magnitude. Okay. But the negative sign will play an important role in how we look at the internal energy of the system changing. But you can definitely tell, right? You can definitely tell that the internal energy of the system should change, because if I change the pressure, even if the volume rather, even if I allow the temperature to stay the same, if it's in some sort of thermal contact with some heat reservoir, then the internal energy should change because the pressure should increase. And as the pressure is going to increase, it's going to increase the internal speed of the particles. Okay, so not the internal speed, but the RMS speed. So be aware of that. Okay, and actually, what I just said is false, because the RMS speed uh, 3 kBT over M. Yeah, no. So it won't increase the RMS speed, but it will go into increasing the internal energy. Okay, so be aware of that. But so that is how you calculate this work. Okay, so the entire idea is that you need to get your pressure as a function of volume to then do this integral. Okay, but this integral is the work done in a thermodynamic sense. Okay, so the idea being, get your pressure as a function of your volume, and if you know the equation that relates those, like the ideal gas law or the van der Waals equation, then you can easily do that. The van der Waals equation is a little bit harder to integrate, so be aware of that, but you can still do it in principle. Okay. But that is an introduction to thermodynamic systems and work, and in the next video we will discuss the first law of thermodynamics.